Hey guys, this video pertains to principal component analysis and factor analysis, and what I intend to do in this video is show you how to carry out these techniques using R. So the data set we have in front of us is something that I quickly generated from a placement testing program that we use, and it breaks students' scores down across calculus, trig, problem solving logic, statistics, and algebra. And if you come on down, I don't know how many people we got here. It looks like we have about 73 students. And this would be something that may be appropriate to use factor analysis because, you know, again, factor analysis, there's a lot going on, but at the end of the day, it's a reduction process. We want to look at underlying factors. We want to see if these things, these variables, calculus, trig, and so on, may be related in some way that we can't see just simply eyeballing. So it gives us a pretty powerful tool. Something else to keep in mind, I've kind of fabricated some data for the second part of this video, and I'll explain that in just a second. But you know, if we wanted to include this data in a linear regression analysis, we're slightly restricted because, well, there's varying rules out there, but typically you can think of about, you know, needing about 25 cases per variable if we're going to use, you know, so many variables in our analysis. So in this case, with 6 variables, we would need about 150 subjects to be able to include all 6 if we were going to conduct regression analysis. So this may be some place where we can look for underlying factors and actually combine things and create new factors, which we may be able to give names if we can see patterns emerge, and get this thing down to a couple, 3, maybe even 4 factors that we could use appropriately in regression analysis. But I'm going to demonstrate all that. So guys, the first thing I want you to notice is to save time, I have already set the working directory and brought the data into R, and I've attached it, which is cool. Next thing I want to do is I want to get the names of my data, and I just want to have those there because we know how, you know, if we're off just a little bit, R's definitely going to point it out to us. Guys, first thing I probably want to do is I want to do a correlation matrix, and I want to look at the correlation between the variables. So when I just eyeball this, I get a 0.74 correlation between trig and calculus, and I get a 0.72 correlation between algebra and calculus. That leads me to believe that people who do well in calculus tend to do well in trig and algebra, but not so much with stats, logic, and problem solving. So that leads me to kind of want to investigate, are these things, problem solving, logic, and stats, related? So I could come over here to this column, logic, and come down to problem solving, and we see we have almost a 0.5 correlation, and statistics has a 0.48, but low correlations with the others. So I'm kind of tending, I tend to believe, or I'm led to believe right now, that we might get some factors that emerge across calculus, trig, and algebra, and then another factor that emerges that includes problem-solving logic and statistics. And if you could see the underlying factors there, calculus, trig, and algebra are pretty, I guess you would say, algebraic intense, or at least require symbolic manipulation, more so than problem-solving logic and statistics, which kind of more mathematical reasoning, if you will. So that's what I'm kind of thinking is going to happen. But you know, let's let it happen. Something else we may want to do is go summary of our data, and this is going to give us some the 5-number summary plus the mean. I wish they included the standard deviation or variance in this, but they don't, and they haven't asked me either. So, but But what I want to do here is just kind of focus on the mean rows. And what I see there is I see that the mean has, kind of, I don't know, I guess as expected, was the lowest for calculus. And it was the highest for logic. Okay, that's a little shocking to me. It's relatively low for problem solving, and it looks like statistics and logic are the two highest averages. So guys, the first thing, excuse me, first thing I want to do is run my principal component analysis. So I'm going to be real creative here and call this PCA. And the command on R is PRINCOMP, and I want to tell it that I'm going to use data, the data set that I have stored, and then we do scores that's not right, equal true, and we want to do the correlation matrix instead of the covariance matrix. Now, if we run a summary on PCA. Now, something to keep in mind with PCA, principal component analysis, is you're going to emerge the same number of components that you have variables. And notice up here we have calculus, trig, problem solving, logic, stats, and algebra, which give us 6 variables. So we are going to end up with 6 components. What we're trying to do here is we're trying to decide how many components describe the appropriate proportion of the variance. Well, I don't say appropriate because this is all a subjective determination in the end. So a pretty common rule is to look at the variances, and we call those eigenvalues in this situation, which would just be the standard deviation squared. So if I take 1.76 and square it, I get 3.10, which I'll talk about in just a second. And if I square this, I get 1.34. And if I square 0.74, I get 0.5476. Now, kind of a rule of thumb is we want to focus on the components. We want to reduce this. This is a reduction process. We want to reduce this down to the number of components that adequately describe the cumulative proportion of variance. So kind of a well agreed upon rule, at least the way I was taught. And my folks came from University of Chicago, so hopefully they hopefully they taught me well. Was to look at the variances which were above 1. Well, when I square 1.76, I get a little bit above 3. When I square 1.16, I get 1.34. But the next one I score, square, 0.74, I don't get 1. So what I'm looking at here is I'm going to look at the potential for a two-factor model. Good gosh, a two-factor model. And again, notice these things are descending. So once I find the first one squared that doesn't create a value greater than 1, then obviously none of the others are going to create it that way either. So at this stage, it's kind of interesting to create what's called a scree plot. And a scree plot's really easy to create. Just type plot, and our model is called PCA. And what you can see is the vertical axis gives us the variances, which I squared right over here. Oh, I didn't want that to happen. I never will find that. Well, all right, where did the thing go? There it is. All right. Let me hear a scree plot. Okay, so now I really want that up in the background, but it's not going to allow me to do that. All right, I'll tell you what, this thing's being crazy, so let's just start over. Because I want you to be able to see this and where I squared. So notice 1.16, which was the standard deviation of component 2, when squared gave us about 1.16. No, I'm sorry, 1.34. Now, there's a way to look at points of inflection, and I'm not going to get into that, but if you look at the drop-off from component 1 to component 2 and kind of the leveling of component 3, 4, and 5, and 6, it kind of leads you to believe that we need a two-factor model to describe this relationship. So another, at least in my opinion, probably the most useful in making this determination is something called a biplot. Now, it's probably going to take a little while. No, actually, it didn't take a little while. Now, what this does is it looks at these vectors, and it looks at the ones that are highly correlated. So you're kind of in a give and take here. You want to find things that are highly correlated, but you want to separate the variance in the so-called components. So it looks like to me that algebra, trig, and calculus are these vectors right here, and notice how they're all pointing in the same direction, relatively speaking. Problem-solving logic and stats are all pointing in the same direction, which leads me to believe that they're loading on one factor. So it looks like to me we've got a classic two-factor model here with problem-solving logic and statistics loading on one factor, and right now we're calling them components, but we'll be moving into factor analysis here soon enough. And it looks like these vectors are loading on the what I'll call the trig, algebra, and calculus. So let's. There's something I'm not going to get into this right now, but we can. If I go PCA $ loadings, I get the component loadings. These are just the correlation between the variable and the component. And as I look down through here, you know, what jumps out to me again are the 0.4s are the ones calculus, trig, and algebra. And then when I get to component 2, I get the highest correlations of problem-solving logic and statistics. I'm pretty going you know, Mach 2 speed here on working with two factors. All right, one more thing, we can get the scores, and these are just the scores for the PCA. All right, and let's not worry too much about those just yet. All right, gang. I'm feeling pretty good about this two-factor model, so now I'd like to go in and kind of test it. And what I'd like to do first of all is just I'm going to do my factor analysis. So I'm just going to call it factor. No. Let's call it model 1, because we may end up doing a couple models. All right. Okay, I forgot how to do this. No, I didn't. Okay, we run a factor analysis. It's kind of as you may think. And what we want to do is we want to test the number of factors, and I'm going to propose that two factors adequately describe our model, our relationship. And we're going to use what's called a Varimax rotation. It's one of many, but Varimax I think is by far the most commonly reported. Now, let me show you. You really, in this case, don't want to do summary of model 1 like we usually do. It gives us stuff that I don't know what it gives us. But all we need to do here is just go model 1. And we start to get a lot more important information. Now, at the very bottom is probably one of the first things we'd want to look at. And what our null hypothesis is in this process is the two factors are sufficient, and the alternative hypothesis is two factors are not sufficient. So in a sense, if we're really buying into this two-factor model, we want to fail to reject the null, which at the 0.05 level you can see that we did. We have a chi-square statistic on degrees of freedom 4. And right now I'm most interested in coming back up and looking at the summary of my loadings. which is right here. And I want to focus on factor 1 right now. And the highest correlations with factor 1 tend to be calculus, trig, and algebra. The highest correlations with factor 2 turn out to be problem solving, logic, and statistics. Notice statistics didn't even load on factor 1. And of course it emerged with the highest correlation with factor 2, which is not surprising. Okay, let's go ahead and run. Let's run model 2, and let's run this again. Same stuff. But this time I want you to come in and type scores equal regression. This will kind of go do some cool stuff. All right, gang. We still get the same regression. Actually, I wish what I'd done is run the initial model. Let me do that. Let's do the initial model without rotation. This is something you wouldn't do, but I want you to see it. So factors risk 2 is sufficient. But let's do rotation equal none. And if we do an initial model, what you'll see is well, statistics actually ends up loading on factor 1. But as we perform rotations, we expect to get a better model. In other words, we expect to increase the correlations on factor 1 and factor 2 of the variables that we expect to, or end up finding out, load on those factors. So calculus was 0.863 in the initial, and it actually went down a little bit, so it's kind of proportioning out the variance. See what happened with problem solving. It was 0.258. It was 0.50 in the initial. So it's attempting to kind of level out. I'm a little bit surprised by that. But there's... okay. I thought this would make things clear. In this situation, it doesn't. Typically, what I expect to see in the initial model is lower correlations, and then we rotate. I expect to see higher correlations on the factors. We see a little bit of that here on factor 2, because problem solving started at a 0.499, and after we did a rotation, it goes to 0.658. Logic increased substantially, and statistics increased substantially. But the factors on after the rotation, the factor 1, they went down a little bit. So okay, but you know, ultimately, what I'm wanting to see is you know, what you know, how many factors, and we kind of search for the least number of factors that adequately describe the underlying patterns. And I'm pretty happy in this situation with a 2-factor model. Okay? Now, let's put this to use. Most people agree, well, actually they don't agree, I don't know what I'm thinking about here. It's up for a lot of debate depending on what textbook you look at. Pethazer says one thing, and Tabish, and Fidel, or if that's the way you say that. I've never understood how to pronounce their names. They give another, I think they give a 104 plus K, or like a 52 plus 8K or something like that. Anyway, how many cases do we need per variable for regression? Now, a good rule of thumb there is that we need 25 cases per variable. So if we had something we were wanting to predict with this data set, and let's go all the way back up to the data, to the names. we have 6 variables here that we may want to include in some future analysis. And if we go by minimum standards of 25 cases per variable, then we'd need 6 times 25, which is 150 cases. Well, I haven't shown you the data yet, I don't think, but yeah, I actually did. I showed you earlier. So we have 73. So according to the the minimum of 25 cases per variable, we would at most be able to include approximately 3 predictors. But we got 6. We have 6 things that we'd like to include. So in this situation, I like factor analysis. It's probably one of the few situations I actually do like factor analysis, where I think I can, collapse trig, calculus, and statistics into one component, one factor, and problem-solving logic and algebra into another. Now, I want to show you how we could do that. So let me go back to the data. And what I actually have, you'll notice this is a different data set. The calculus scores, trig scores, problem solving, and so on and so forth, which are components of our placement test, now are the same, but now I have some ACT scores. Now, I wish I had the ACT for these students. I got to admit to you, I created these scores right here randomly, so I'm expecting to find no patterns whatsoever. I did this just for an illustration purpose. So let's say that we did want to take the calculus, trig, problem solving, logic, statistics, and algebra components and use those to predict how well students are going to do in their ACT. Well, again, I've got 73 subjects according to the 25 variable rule, 25 cases per variable. I would need 150 cases. Well, I don't have that. I've got half of that. So what I may want to do here is I may want to come in with factor 1. And let's call factor 1 the symbolic manipulation factor. And that was the variables calculus, trig, and statistics that loaded on the factor that required symbolic manipulation. So guys, what I may want to do here is to take the average of these 3. And it's not going to let me click that box it's going over, so that's going to be what, G2. So the average of those scores for the algebra, again, the 3 variables that loaded on that factor. So I'm using that to combine. And I'm going to get this down to where it's not so messy. All right, so I'm going to do a fill down. So I'm using the average of the scores of the variables that loaded on that particular factor. Now, factor 2, I would probably give that the name, mathematical reasoning, if you will. I'm not really sure. But that turned out to be the problem solving, the logic, and the statistics. Again, clean it up because these kind of things bug me. Alright, let's fill down. And I've created 2 new factors. And again, these factors are kind of underlying, describe underlying relationships, things that we can't eyeball, and just as I've explained. Now, I wouldn't be afraid to save this, and I'm going to save it as, let's see, what did I save it as? I think I just saved it as, called the other one Math Skills. So this one's Math Skills 2. So guys, I wouldn't be afraid to, if I wanted to use some sort of model to predict ACT. And again, guys, we're not going to find anything because the ACT scores were randomly generated. And let me show you how you can do that just for the heck of it. Now, if I wanted to generate some ACT scores, and in this case I wanted to generate 73 random ACTs, now I can use what's called R norm. R means random, and I want 73, so you tell R how many you want at the beginning, and then you tell the mean, which 20.6 and 4.8 would be the standard deviation of the distribution I wanted to create. So I want to pull out 73 observations randomly. It's kind of pseudo-randomly. I'm not buying into any true random number generator. With a mean of 20.6 and a standard deviation of 4.8. Now, if I type ACT, it'll show you the 73 scores that it's so-called randomly generated. And it's my understanding. I'm far from an expert on random number generators, but I've been to talks of people who are so-called experts on this, and it seems to me that a lot of people at least feel that once the algorithm starts, then it does a pretty good job of generating things randomly. The problem is it doesn't start randomly, if that means it makes any sense at all. Now, what I could do here, let's just take the mean ACT, 20.1 or 21.11, which that's cool, and take the standard deviation of ACT, so they fluctuate just a little bit. Now, if I took another random sample, and this is something really cool for you guys who are going to be teaching statistics in our dual credit, you could take multiple samples and show that our first sample is 73, has a mean of 21.11. Our second random sample has a mean of 20.78. So this is really, really cool. And let me just show you the standard deviation. It's going to vary as well. Wow, it didn't vary. Cool. Sort of. Well, that's interesting. So, but you could. This is a really nice transition into the central limit theorem, and stuff. So let's go back to what we were doing before. Okay. So I want to bring in a new data set, and I'm going to call this my second data set 2, and I want to read CSV, and I think I called this one Math Skills 2.csv, right? And obviously I want to attach it. And there's some data, okay, so I probably would have been better off to have closed down and restarted, but I think we'll be fine. So guys, if I wanted to do a model, let's just call it a linear model to predict ACT from, yeah. Hold on. Let's get the names up there. Okay, so all caps. All right. So if I want to create my linear model to predict ACT from the factors, I can do that. So I could do summary, and you guys probably remember that, or at least I hope you remember this from 5500, and we could get our coefficient table, and we're seeing no statistical significance, which we really wouldn't expect to see that because, again, I randomly generated the ACT scores. So guys, again, these other scores actually did come from something real. The ACT scores were just a figment of everyone's imagination. So, and you can see where this could kind of get headed. We could, go in and look at a t-test of factor 1 and factor 2, and we could go crazy places. So, if we had maybe 3 factors, we may conduct an ANOVA some mean over the factors. So, guys, that's about all I have. Again, this is in the spirit of what we're trying to accomplish in this class. I want to keep this simple. And in your master's thesis, if you would happen to find the need to conduct PCA and factor analysis, then we'll get a lot better at it at that time. But that just depends on where you're headed. So right now, I'm just wanting to give you all these kind of these statistical tools that are often used in education research. Kind of wet your whistle, get you aware that they're out there. So when you're developing your research thesis, when you're developing your research statement, you can looking at your methodology and coming up with your instrumentation. You'll realize that this stuff exists. So, guys, that's all I got. I'm kind of rambling now. So that's it. Have a good one.